So if I told you to go out and buy an HDMI cable right now, you'd probably drop, I don't know, maybe 15 bucks.
Yeah, 15, maybe 20 if it's a nice one.
Right, and you plug it in and literally never think about it again. But today, we're doing a deep dive into this spec sheet for a cable from a company called DVIGear, and commercial engineers are out there casually spending over $1,000 on a single one of these.
Well, it completely redefines what a simple cable actually is. We're looking at the DVI-2590-AOC today.
This is quite the name, yeah.
Right, it's an active optical cable, and really it's just a masterclass in extreme engineering. The mission of our deep dive today isn't just about, connecting a screen in your living room. It's exploring how you can instantly move massive amounts of high-resolution video data across these colossal physical spaces without dropping a single pixel.
And to understand why a cable like this even needs to exist in the first place, you really have to look at the physical limits of a standard copper wire. Like if you try to push a massive 4K video signal through standard copper over a really long distance, it's like trying to blast a fire hose of water through a standard garden hose.
Exactly. The resistance is just way too high.
Right. Over 5 feet, sure, the signal is crystal clear. But over 300 feet, the electrical resistance turns that signal into absolute noise. It just degrades and completely dies.
And see, that degradation is exactly where the active optical cable, or the AOC, steps in. So DVIGear solves this bottleneck by actually translating the heavy video data into light.
Which is wild to think about.
It really is. But it's a hybrid design, right? So you have 4 distinct channels of what they call polyfluorinated optical fiber, or POF, and those are sitting right alongside 6 traditional copper wires.
Wait, let's look at that POF acronym for a second, because I think I just had an aha moment reading the specs. The P stands for polymer, right? Like plastic, not glass.
Yep, exactly. It's a plastic fiber.
Okay, so that totally explains the physical specs further down the page where it mentions a tiny 2mm bend radius. Because, I mean, if this were a standard glass fiber optic and you tried bending it around a really tight 90-degree corner inside a wall, it would shatter instantly.
Well, 100%. It would just snap.
But because it's polymer, it actually flexes.
And that flexibility is a massive advantage for installation. Those 4 polymer optical channels actually use these tiny micro lasers to fire uncompressed 4K video at 60 frames per second, literally at the speed of light.
That is insane.
Right. Meanwhile, the 6 copper wires, they just handle the basic electrical handshakes. We're talking about things like EDAID, which tells the video source what kind of display is actually connected, and HDCP for the anti-piracy copy protection.
Right, because copper is perfectly fine for those sort of basic low bandwidth signals.
Exactly. You don't need lasers for that part.
Okay, well, here's where I still get a bit skeptical about that $1,000 price tag, though. You're running actual lasers inside this cable to shoot data up to 100 meters, which is, by the way, longer than an entire football field.
Yeah, 100 meters, or up to 328 feet, yeah.
Right, and lasers need power. But I'm looking at the specs, and it says this requires 0 external power supply. Like, there's no bulky power brick you have to plug into the wall. How on earth is it pulling off laser transmission on literally 0 power?
Well, okay, it's not exactly 0 power. It's just incredibly, incredibly efficient. See, standard HDMI ports actually have a built-in 5-volt pin that's designed to power tiny internal chips.
Oh, okay. I didn't realize that.
Yeah, so DVIGear basically engineered the transceivers inside the cable heads to operate on just a tiny fraction of a watt. So they basically sip just enough electricity directly from the TV or the computer port to fire those micro lasers.
So you're getting 18 gigabits per second of total data over 300 feet. Completely interference-free just by plugging it in normally.
Yep, exactly. Just plug and play.
But going back to that $1,065 price tag,
yeah.
I mean, even with the clever power draw and the fancy plastic fiber, going from 15 bucks to $1,000 is a massive leap. I'm still not entirely sold on why, like, a sports stadium or a hospital needs to spend quite that much on one cable.
Well, it really comes down to the fact that failure just isn't an option in those environments. And you need incredible physical toughness to guarantee that. Just look at the crush resistance on this spec sheet. It's rated for 500 newtons.
Wow, 500 newtons.
Yeah. In the real world, that basically means a 250-pound contractor carrying heavy gear can step directly on this cable in heavy work boots, and the video signal won't even flinch.
Okay, I get it now. So it's essentially indestructible infrastructure. And I see here the jacket is plenum rated too.
Yes, which is super important for commercial stuff.
Meaning, if I understand right, if you run this through the air ducts of a giant corporate skyscraper and there's a fire, the cable itself won't melt and release toxic gas through the HVAC system. So you aren't just paying for the bandwidth.
Right, you're paying for extreme durability and strict building code compliance. Delivering flawless digital experiences in the real world isn't just about, smart software.
Right, it takes serious physical hardware.
Exactly. It requires a pretty miraculous blend of fiber optic light transmission and really heavy-duty mechanical engineering. Ultimately, this cable is the invisible backbone that keeps those massive commercial displays running flawlessly 24/7.
Seeing the sheer scale of the engineering required just to get a reliable 4K picture across a building really makes you think about what's coming next. I mean, we are already shooting massive data signals via light over 100 meters just to power today's flat screens.
Yeah, it's pretty incredible when you step back and look at it.
So if this is the kind of heavy-duty infrastructure required right now, what kind of invisible, ultra-high bandwidth light pipe networks are we going to need hidden inside our walls to support the truly immersive holographic environments of the future? It's wild to think about.